Okay folks, welcome to the bathroom. So what this video is about is just a little bit of a tutorial for your Matrices test on Tuesday week. Your assessment is going to take, what it's going to be is there's a summer 2020 exam paper that's already been written for your module, but obviously you're not going to sit that exam. We're going to break it up into some tests, and your test on Tuesday is going to comprise the Matrices question. Now that means the exam is 2 hours, each question is worth the same, so the question is designed to be done in about half an hour, but you're going to have plenty of time in the remote assessment to do it. So by way of revision, what we're going to do is I'm going to go over the 2019 paper, the question 2, it's on page 223 of your manual, and we'll just do some kind of general exam hints. I suppose we'll do a question and then we'll kind of see what I'm talking about as we go. Okay, so the first one is question A. So what we have here is we're given a 2x2 matrix. And what we're asked is to investigate, of course you have the question in front of you, hopefully, if you don't, pause the video and go here in your manual. Investigate is A inverse transpose equal to A transpose inverse, and is A squared inverse equal to A inverse squared. So this is, in the technical language, it's saying does inverse and transpose commute, and does squaring and inverse commute, in this case. Okay, so okay, so off we go, I suppose, with part 1. Now we're asked to show that one thing is equal to another thing. So what we should do is to find, we don't assume they're equal, we go off and calculate some things. So first of all, we're going to calculate A inverse. Now A inverse, I'm going to have to send you tables with formulas for your assessment, and I think I've sourced a copy of the state examination table, so they'll do the job, and they'll have in them that the inverse of a 2x2 matrix is 1 over the determinant, right down diagonal minus left down diagonal. Swap the entries on the right down diagonal and change the sign on the left down diagonal. Okay, so that is a formula that you'll need from the tables. So we'll calculate the inverse of this. We're about to calculate A inverse transpose, so first we must do A inverse. So 1 over right down diagonal is 2 by 3, which is 6, minus left down diagonal is 5 by 1, which is 5, and then I swap the right down diagonal, so instead of 2 and 3 it's 3 and 2, and I change the sign on the other diagonal. Okay, now it's probably just worth remarking here, I don't think these things are equal in general. In particular, I think sometimes you can have I'm not sure, doesn't matter for the purpose of this assessment anyway. Now this is 1 over 1, which is just equal to 1, and 1 over 1, yeah, equal to 1, so we have 1 by this matrix, which is just itself. Okay. And now let's calculate the transpose of that. So therefore, A inverse transpose equals. So the transpose for us is just another matrix found by swapping the rows and the columns. So the first row 3 minus 5 becomes the first column 3 minus 5. The second row minus 1, 2 becomes the second column minus 1, 2. Okay, we'll let that sit for a moment. And now we're going to do it the other way around, that we do the transpose first. So starting again, A transpose, first row becomes the first column, second row becomes the second column, and now we find the inverse of this using this formula here. So we do 1 over right down, 1 over the determinant, which is 2 by 3, which is 6, minus 5 by 1, which is 5. Then what we do is we swap the entries on the right down diagonal, 3 and 2, and then you change the sign on the other diagonal. Okay, Now this again is 1 over 1, which is just 1, and 1 multiplied by any matrix is itself. So this is 3 minus 1 minus 5, 2, and indeed transposing first and then inversing is the same as inverting and then transposing. A good question for you to think about more generally, is that always true? I believe it probably is. Yeah, it is, because the question is, the only possible thing that's going to go wrong is that maybe A is invertible but A transpose is not, but A and A transpose have the same determinant, and that means if one of them has a determinant of 0, the other does, and having a determinant of 0 is the only way that they can be not invertible. So these are actually always equal. Okay. Right, let's look at the second one, which is to show that A squared inverse is the same as A inverse squared. Again, I actually think this is always true, but you'd be worried that maybe squaring something makes it invertible when it isn't previously. Yeah, we won't worry about that. Okay, so first of all, we're looking at A squared inverse, so we'll calculate A squared. Now, one thing to look out for is A squared doesn't mean put some 2's on these, it means A by A, which means 2, 5, 1, 3 by 2, 5, 1, 3. Now, obviously, my space is a little tricky here, so I'm going to go as small as I can. If I multiply matrices, remember that what you need to do is look at the sizes of them. This is a 2 by 2, and this is a 2 by 2. And because these middle numbers match, you can multiply them together. Does make sense. And what you're going to get out is a matrix that has size 2 by 2. So that's what I'm going to set up here. And then I recommend celling this up. So 2 rows, 2 columns. And I'm going to go a little quicker than I'd like here. So this is row 1, column 1. So I multiply row 1 by column 1. So 2 by 2 is 4, plus 5 by 1. 4 plus 5 is 9. I probably have space to do this sum. Okay, so it's 2 by 2 is 4 plus 5 by 1. Yeah, sure, we may as well. Plenty of time anyway with everything going on. So 2 by 2 is 4 plus 5 by 1 is 5. Okay. Then here this is still row 1 but column 2, so you multiply row 1 by column 2. 2 by 5 is 10 plus 5 by 3 is 15. Now here, this is row 2, column 1, so I do row 2 by column 1. 1 by 2 is 2, plus 3 by 1 is 3. And this is row 2, column 2, row 2, column 2. So I do row 2 by column 2. 1 by 5 is 5, plus 3 by 3 is 9. And I can tidy that up here, I suppose. That's the matrix 9, 25, 5, and 5 plus 9, I think, is 40. Right. That's A squared. Now we want to go on to calculate A squared inverse. So using this green formula here, do 1 over right down diagonals minus left down diagonals. 9 by 14 is 140 minus 14, which is 126. Take away 5 by 25, which is 125. And then we swap the right down diagonals, 9 and 14 become 14 and 9, and change the sign on the other diagonal. Now what you're getting here is the determinant of this is 1, and if you think about what we said, the determinant was as a scale factor. If you apply the matrix once and it doesn't change the area or the volume, and you apply it again and it doesn't change the area again, well then the determinant of A squared will be 1. Okay. So this is 1 over 1, which is 1. So you get 14 minus 25 minus 5, 9. And we're wondering, is this the same as A inverse squared? Now luckily we've already calculated A inverse. So we can calculate kind of directly A inverse squared is equal to this by itself. Okay. Right. So again, I recommend looking at the sizes. Sorry, I keep thinking about whether these two are always equal. It's not too important for us. It's a good problem for you to think about. If you have any thoughts on it, you can send me an email. It's not that hard to figure out, but it is while you're doing the question. Okay, so you get a 2 by 2. And of course, if you want to prove it, so I'm trying to just prove it using kind of geometry in my head. If you really want to prove it, you can do it with a general A, B, C, D. Just look out for division by 0, etc. Okay, so, oh yeah, we said, okay, we can multiply these two together because these numbers are equal. The outside numbers are 2 by 2, that's the size of this. And now we multiply rows by columns. This is row 1, column 1, row 1 by column 1. 3 by 3 is 9, plus minus 5 by minus 1 is 5. And then this one is row 1, column 2, row 1 by column 2. 3 by minus 5 is minus 15, plus minus 5 by 2 is minus 10. And this one is row 2, column 1, row 2, column 1. Minus 1 by 3 is minus 3, plus 2 by minus 1 is minus 2. And finally, row 2, column 2, row 2 by column 2. The multiplying in the sense of dot products, minus 1 by minus 5 is 5, plus 2 by 2 is 4. Let's see how this works out. 14 minus 25 minus 5, 9, which is equal to this, happy days, which is the same as A. So this is A inverse squared is equal to A squared inverse. Happy days. So that's the first question done. Now, in terms of exam technique here, you can't really check your answers. But what you can say to yourself, have I answered the question that was asked? And the question is, investigate if these are true. These little ticks show me that you understand that these things are equal. So these statements, in this case, are true. Good job done. Okay, we'll move on to question B. So question B has a diagram where it's a force diagram. And I think the magnitudes of the forces are not given. But what is given is the angles between the forces with respect to some axes. And if you write down, okay, so you want to say for equilibrium, the sum of the forces is 0. So that means the sum of the forces in the vertical direction is 0 and the sum of the forces in the horizontal direction is 0. And that gives you two equations in two unknowns. And we do have two unknowns here, the magnitudes of the two forces. And it says that the two magnitudes of the forces satisfy simultaneous equations, which are given as 39F1 minus 60F2 equal to 0. So I think they're the forces in the vertical. And then 52F1 minus 25F2 equal to 650, which is the sum of the forces, I think, in the horizontal direction. The question is, write this as a matrix equation. So this, okay, so this is something you either know or you don't at this stage, I suppose. So you can write it as 39 minus 60, 52 minus 25. So that's the matrix of coefficients multiplied by the vector of unknowns, which is F1, F2 equal to 0, 650. So have we written the linear system as a matrix equation? We have. Maybe it's worth annotating what we're doing here. This is AV equal to B. Matrix of coefficients, vector of unknowns, vector of, I suppose, constants. And it says, hence, use the matrix inverse method only. Now, hence means you have to use this. Only says if you don't use it, I'm not giving you any marks. Find these two correct to three significant figures. Now, this problem, should you attack it using matrices? No, you shouldn't. You should just do basic simultaneous equations. But I'm interested in examining, do you understand what the inverse does? Okay. So what we're going to do is we're going to solve this little thing as a little matrix equation. And the question is, you're trying to get the vector of unknowns, F1 and F2. So you need to get rid of this multiplying by A. And to get rid of multiplying by A, you undo multiplying by A, you multiply by A inverse. So what you do is you multiply by A inverse, and you have to be careful. If you can't multiply in here, that because these are multiplied together. You could multiply here by A inverse on the right on both sides, but that A inverse cannot kill that A. You have to multiply on the left on both sides. You can't multiply A inverse here and A inverse here, because the order of multiplication of matrices matters, and multiplying on the left is not the same as multiplying on the right. So you must multiply both sides on the left. So you get A inverse. So if I was to write down what we're doing here, we're multiplying by A inverse on the left. You could write something to signify that. AV equal to, so let's multiply the left hand side and also multiply the right hand side, B, and then multiplying A by A inverse undoes the action of multiplying by A. So you just get V is equal to A inverse B. So we have to find the inverse of this times this is all we have to do. The inverse of a matrix, a 2 by 2 matrix, we saw it on the previous thing before I wrote it all out. So if you look back at that formula, it's probably on your page, you should be happy enough to see, okay, 1 over right down diagonals, 39 by minus 25. Now that'll be minus 975. I really should check that, shouldn't I? No, I'm happy enough. 40 by 25 gives you, well, 4 by 25 is 100, and then by the 10 you get 1,000, but there's one less, okay. Take away 60 by 52. I could probably do that in my head, but look, I have a calculator right here. Stop being an idiot. 3120. The plus because it's minus minus. Then you swap the right down diagonal, so this will be minus 25, 39, and then you multiply these by minus 1. This is the real thing I'm interested in here, by the way, so there'll be good marks for this. Okay, so V, in other words, what we're looking for is this, which is A inverse, times this, which is B. So V, therefore, which is what I'm interested in. Now it's going for 3 significant figures, but don't round until the end is what I would say. So 3120 minus 975 gives 2145. The rest of A inverse is here, minus 25, 60, minus 52, 39, times B, which is 0, 650. So we get 1 over 2145, and now these are, we're multiplying, we're doing matrix multiplication, so let's look at the sizes. This is 2 by 2, and this one, pause the video and have a think. What size is it? It's 2 by 1. 2 rows, 1 column. These numbers match, so you can multiply them together, and you'll get out a 2 by 1. Just 2 rows, 1 column. Cell it up is my recommendation, and now let's go. Row 1, column 1, row 1 by column 1. Minus 25 by 0, of course, gives us 0. And 60 by 650, we'll just go into the calculator for that, is 39,000. And then we've minus 52 by 0, which of course is 0, plus 39 by 650. And it gives 25,350. So this is, you've got 39,000 here, 25,350 here, and this vector slash matrix slash list of numbers slash vector of unknowns is multiplied by 1 over 245. Now this is just ultimately a small constant, and when you multiply a constant by a vector, or indeed a constant by a matrix, every entry gets multiplied. So I'm going to have 39,000 by 1 over 245, which is the same as dividing by, well, yeah, by 1 over 245. Excuse me, 2145. So this, now I'm going to do 3 significant figures here, so as an engineer doing equals, that would hurt me, so I need to approximately 18 point, now it says 1/8, and the question says 3 significant figures, so 1/8 will round to 2. And then the other one is 25,350 by that number at the front, and this is giving me 11.81. Okay. Does it say anything about units? I normally don't care about the units here. No, it doesn't say anything about units, so it'd actually be wrong to say newtons here because we don't know anything about the units. What you should do here though, and it makes perfect sense to check your answers. So the question is, okay, so the exam tip is, have I answered the question as asked? Part 1, write the linear system as a matrix equation. Done. Part 2, hence, using this, I did. Use the matrix inverse method, I did. To find F1 and F2, well, look, V is F1 and F2, that's F1 and F2, find it. Now, the next thing you do is, does your answer make sense? These answers, if you look at the picture, they make sense, but you can actually check your answer here. You can back substitute these in here. So I got 39 by 18.2 minus 60 by 11.8. Now, will you get exactly 0? No, because of the rounding here, I get 9/5. Now you might think, oh, that's a little bit off, and you can be worried about it. Well, that's